embedded in the same plotting space. And so we have even commercial offerings where we made a customized product for someone where it uses this. It uses elements that are pulled from Charcoal for doing very fine rendering, and then you use the 3D rendering engine of OpenGL to actually do the heavy lifting for whatever you want to visualize. Okay, so having done that, how is all of this architecture? So if you look at Maya itself, the toolkits that we usually use are either WH Python or Qt Core. Python forms the basis. I mean, we're writing all of this in Python. VDK itself is a 3D visualization library. How many of you have heard of VDK? Okay. So VDK is a C++ library. We have about 900 plus classes. Huge. They do a lot of visualization, image processing, and graphics. But unfortunately, its API is very C++ish. You have Python wrapper. So TVDK basically marries VDK, NumPy, and traits. And traits is like the cornerstone of VDK. And I will show you a lot of examples and information about traits as we go this. So TVDK is essentially traded VDK. And what that allows us to do is it gives us a lot of power to interact with these VDK objects. And then sitting on top of that is the Maya engine, which is an object-oriented interface, object-oriented structure where we interface with the visualization system, which uses TVDK and traits. Then on top of that is the Maya application, which uses something called Elysis, which is a plugin framework. So with the plugin framework, how many of you have heard of Eclipse? Wow. How many of you know that Eclipse is actually not an IDE, or it's also an IDE, but the IDE is secondary and it's actually a framework? Okay, reasonable point. So Eclipse is actually a framework, so you can build arbitrary applications in Eclipse. It's a really fantastic framework. So Envisage takes a lot of ideas from Eclipse and is completely written by it. So what we do is we use Envisage, like a part VDS, to build the Maya application. Remember you saw the application had panels on the left, it had a window on the right, it had a Python interpreter on the bottom. That is created using Envisage. It's put together using Envisage. But the components are themselves based typically on traits. And then we have a scripting layer on top of this, which allows you to do one-line plots per lambda. So that's kind of the layered architecture that we have with Maya. So EDS in summary has a bunch of components. The core would be traits. Sitting on top of traits is a traits UI component, which basically lets you do very simple UIs, and I'll show you a lot of demos of that. And then you have Charcoal. Again, I've shown you a simple example with that embedded block, but Charcoal itself has a lot of responsibility. Maya itself, and Envisage. And we have a bunch of miscellaneous libraries, which are used for various things. For example, the record function. It's not part of any of these, but it is part of the miscellaneous libraries. There's a library called scripting. AppTools.scripting has this thing where you can just say, here's an object, record all the traits, record all the changes on this object, record all these methods on the object, and as you use the user interface, it will automatically generate the Python. Okay? So it's extremely easy to use and deploy in your own applications. So what I'll do next is, I'm now going to move away from doing demos, and I will keep doing this, but we'll now look at building a small application. Again, those of you who have attended the tutorial have seen this before, but I will scrunch it down and keep it very compact. But I will be showing you a lot of code, so if you need more time to look at the code, stop me. Okay? And I don't have to go a little faster. So the basis of all of this, so why am I doing this? The reason is, if I just show you demos, you'll say, yeah, this guy can build his own applications, that's all very nice. I want to give you a sense for, hey, wait a minute, that didn't look so hard for me to do. I could do that. That's the kind of sense I want you to have at the end of this talk. So that you can go out, and I obviously can't cover all the libraries. So I want to give you that feeling so that you can go back, look at the documentation, and build something on your own, if you want. So traits, as I said again and again, is the cornerstone of EDS. And with traits, what we have is a mechanism by which you can define very special attributes of Python objects. They're just normal attributes, but they have special properties. So here's a simple example. I'll walk you through the code and then show you an actual live running. This is an entire self-contained Then you can say application, but it's too stupid to say an application. This will not online. So first import, read, and then you define a class called person. In this case, I'm talking about a person, and the person has traits. Right? We have implemented from the person has traits. Has a name grade, which is a string. Right? Has a sex, which is equal to male again, and has a weight, which is equal to male. Okay? Now, as the weight changes, I would like to do something. For example, we have 80 kilos. I may want to say, hey, you're getting fat. We can. So, this is a way by which I can add a little handler. As this weight is changed, it will run this code. Okay? So, it will say, hey, the weight is greater than 80, what's your weight, buddy? It should print that. So, let's create one of these functions. I'm saying t is equal to person name. It's the same way as you do it with type. Except that this is fairly readable, right? You can read it and say, how many of you have done Django programming? So this looks very much like a model, right? But this predates Django, by the way. So this again uses the same idea that you basically declare your attributes a priori in the class declaration. So you don't have to invent none of that mess. The last line you see will actually give you a user interface for free. So let's see how this works. There's the code. I'm going to run it. So that's my free user interface. I can select between male and female. And let me move the weight. So it's now hitting 79, 80. And look, as I drag this along, it's going to start saying, what's your weight, buddy? Okay? So, it's easy for me to create a simple user interface, and that's all the code I wrote. There's no magic, I'm not cheating here. You can run it on a standard Python interface. So, that's kind of like the power of traits, that you can create very simple classes, and it has a very rich behavior. Look at all the things that you're doing here. I'm saying that, for example, if I were to change, so let me try this, t.sex equals 1. It's going to give me an error, and it's going to be a very descriptive error. It's saying the sex trait of a person instance must be female or male at a value of 1. I think this is right. Okay? Well, you don't know if it was 1, whether it was a string 1 or it was whatever else, right? Whereas if I gave it, that is an acceptable value. So it does validation for me, it does initialization for me, it does notification for me, and it also does visualization. All for free. It's about what? 5, 6 lines of code. So traits happens to be, you can follow that traits happens to be the cornerstone. Everything we build in a thought, commercial, league, typically will have traits. Sitting on top of traits is something called traits UI. So what we do is, you tend to write your models using traits, and then you give it a view using traits UI, which is completely declarative. You basically say, I want to see this element, I want to see it like this, so on and so forth. You don't write any Qt or WXPattern code. I'll show you examples. And so you create the view part. The controller part, sometimes most often we don't need, but if you do, we also have that mechanism by which you create the controller. So you basically, from the ground up, so as a programmer just trying to work on a problem, I work on the model. I get a UI for free. If I want to customize the UI, I throw in a view. Does that make sense? So I can create default views, I can have multiple views, and I can have the views synchronized with the object itself. So for example, if we go back to our little demo, so now if I change say the sex of this to female, let's go back. Notice that it changes on the UI as well. So they're all synchronized. It's not as if that's standalone. You don't have to do any wiring up between that and this. It's automatic. You just change the model, the view listens to the model all the time. Okay? You change something on the view, the model will change. So all of this is kind of hooked up to all you. And as you can see, you can create a UI with minimal toolkit knowledge. You don't need to know much about actual UI. However, the view that I showed you is clunky, it's automatic, You have no control over what was put, what is the order. You may want to put this first, that second, things like that. So with a view, you can actually specify what you want. You can say, no, I want an A first, I want a 6 next, and I want a wait last. And I want to call my dialog box person. Okay? Configure a question or something. You can set it up like this. And view is simply that. That's your view. No UI code. All you need to do is import from Trace UI, view and an item. There are a bunch of other things. I'm just scratching the surface here to give you a feel. So now we'll solve a specific problem. Here's a differential equation. Don't worry about it. I'm not going to get into the details of the mathematics of this. But here's a differential equation. I'll show you how to get the solution using SciPy as well. So differential equation basically governs the rate of change of x, y, and z. So it's saying rate of change of x is this function, rate of change of y is this function, rate of change of z is this function. You can think of it as say I have a particle in space. At each position I define a velocity of the particle. I'm asking the question, supposing I start here, where does this particle go? Given this velocity. Does that make sense? Right? So if I have it every time the velocity of a car, say, I can integrate it in time to give you the final position. So that is the solution. Okay? So you want to place the path of a particle in this system, in the system ordinary. It turns out that ordinary position equations are very general, very useful, blah blah blah. We are not interested in that. We just want to show you a user interface that shows you how you can interact with this. Okay? So here is the solution using SciPy. The first thing we do is encapsulate the differential equation in a function. The right hand side of the differential equation. And just set u is s into y minus x, which is the equation. S into y minus x, rx minus y minus xz, so on and so forth. All this does is it creates a function, encapsulates some of the constants as the arguments, and returns the NumPy array. How many of you are familiar with NumPy? So they're just arrays. Okay? They have very powerful properties. They are very efficient. The underlying code is written in C, so if you do operations with NumPy arrays, they're extremely fast. Unlike this. And then, now that we've defined the right hand side, I need to solve it. This function here, ODE on SciPy, will integrate. So I just give a starting point. Remember, I told you if I have a point. If I have a car, I need to know where the car started from before I can tell you where it ends, right? So I need to give you a starting point. This is the starting point. This C tells us, the solver, to tell me where at what times do I want the solution, right? After 5 seconds, where is the car? After 10 seconds, where is the car? And then you just solve ODE with this function, start value, and the times that you want. And this R will have your solution, and you can plot it with one line in 3D with this code. Very simple, right? Straightforward. And you'll get something that looks like this. It's a very interesting equation. You won't get into that, but it's very interesting. So how would I build, say, a full-fledged user interface where I have this equation, where I can change parameters, where the plot updates, where I have 2-dimensional plots and 3-dimensional plots, and build a full-fledged application using traits. That's kind of going to be the rest of my talk. So the first thing we do is we create a model that encapsulates this differential equation. So again, I'm creating something that has traits. I'm creating the Lorentz equation. That's the equation's name. And I'm creating the parameters as ranges. Range suggests that it varies between 0 and 20, 0 to 50, and 0 and 10. Okay? And these are the default values for that. And then the right hand side is the same code inside that class, nothing else. It's just the right hand side. I don't call it violence anymore. Because I'm generalizing the right hand side. Is this clear? Am I going too fast? Not clear? I can? Yes. Which traits are I going to? Yeah. Are you asking, is it a standard library? It's not a standard library. You have to install it. It's not part of the standard library. You have to install it. You can install it. On most Linux systems, it's available. You can get installed. SAPES. Yes. Just to solve that ordinary, it does the integration. No. SciPy is also, you have to download. NumPy, SciPy, have to be downloaded separately. They are not part of the standard model, standard library. Okay? So all SciPy does was it solved my differential equation for me in that one line of code. I'm just using that. So forget about the ordinary differential equation now. Let's now look at the model. How do I solve the ordinary differential equation? Now again, I put it in a class so that I can configure and customize things. So I say, okay, here's an ODE solver that has states. The ODE is the instance of this state, which should be Lorentz equation. Okay. And has an initial state, which is the start point. P will be the array for which I want to get it. Right? That's all I need, right? Everybody with me? So ODE requires a function to call the starting value and time. This guy encapsulates the starting value, and the rest are starting value and the this guy encapsulates the right hand side, which is equation, starting value and time. Now we need a solution, right? So what RAIDS offers is a mechanism by which you have what's called a property. It's kind of like add property, right? The built-in function property. Right? So property is an array, it depends on, so what does the solution depend on? The initial state, the time, and the ordinary differential, right? Yes? So if I change, for example, the Lorentz equation somehow, I'll have to change the solution, right? And then get the property, I say get solution, return solve. Now solve is simply calling our SciPy. There is nothing fancy here, right? The only thing fancy here is this property. That's the only new thing you've learned here. And this cache property. What cache property does is it caches the solution. Instead of every time computing the solution, if the parameters haven't changed, it will cache it once. And notice the brevity of syntax. Right? I don't have to do anything more than this. This is fully running code. Okay? Is that clear? Now what? Yes. So here I create the Lorentz equation, I create the ODE solver, set the ODE, set the initial state, the time set.